Okay, so we are continuing the discussion on Boolean functions. I introduced the idea of Boolean function. I said it is a mapping from one set. I mean, all functions are mapping from one set to another, but here Boolean function is a mapping from a set which consists of tensor product of t0 and 1. If there are n input bits, then you can write it like this instead of writing all the possibilities of the n bits. Okay, so that will be 2 raised to n. For large values of n, it is really inconvenient to write that way. So it is a mapping from this set. Okay, Boolean function is a mapping from this set to a set which consists of an output which is only having two values, 0 or 1. Okay, the function can only take values which is only 0 and 1. And then depending upon the value of n, I said that the number of possible function can be found out by using a simple formula. For n bit input, we can have 2 raised to n possible Boolean functions. Okay, so that we looked at. And we consider the case n equal to 1, it was 2 raised to 2, that was 4, and then n equal to 2, then it was 2 raised to n equal to 1, it was 2 raised to 1, 2 raised to 2, and for n is equal to 2, you have 2 raised to 4, so that is 16, and n is equal to 3, you have 2 raised to 8, so that is 256. So now we know how to write down those functions, and it is not really practical to write down all the functions for the cases where n is greater than or equal to 3. Okay, so now the representation of the Boolean function, one way is that it can be represented by using truth table. Okay, representation of Boolean function. So there are multiple ways you can represent a Boolean function. Number one, you can represent it by using truth table. We have seen that for lower values of n. And then secondly, you can represent Boolean functions by using Boolean expressions. So Boolean expressions will contain basically binary operations in the Boolean algebra, which is basically dot operation and plus operation. Okay, dot means we are talking about and operation, and then or operation. So Boolean expression in general will contain or operation. These are binary. This is a binary operation. Then and is another binary operation denoted by dot, and then complements. Okay, so you can write this in this way. Now Boolean expressions can, for a given function, can be written in multiple ways. Okay, so that is what we would like to look at today. So first we will start with truth table. We will consider some random function. Say let's take f of a, b, c. That is a 3 variable input, and we will take one particular function out of all the 256 possible functions. So it is so I'm going to take one of the 256 possible functions. So if I write it in terms of a truth table, then a, b, c, these are the inputs, and now input can take all different possibilities. So this is a 3 variable Boolean function. Okay, so this is f of a, b, c. Now a can take 0, b can take 0, c can take 0. This is one of the 8 possibilities. Now if I have to write the truth table, I need to exhaust all the possibilities. 0, 1, 0, 0, 1, 1, then 1, 0, 0, then 1, 0, 1, 1, then 1, 0, then 1, 1, 1. So these are the 8 possibilities at the input. Now each of the 8 possibilities I can have either 0 or 1. Okay, so depending upon the way I put 0 or 1, I get a unique function out of the 256 possible functions. So how does the 256 possible function comes? Because I can put a 0 or 1 in the first row. Similarly, I can put it 0 or 1 in the second row. In all the 8 rows, I can put 0 or 1. So it is basically 2 into 2 into 2 into 8 times. Okay, so that is 2 raised to 8. So that is how we have 256 possibilities. But I am going to take a particular possibility. Let's say, let me put 0 here, 1 here, 1 here, 0, and then 1, 1, then 0, 0. So this is one of the 256. Out of 256, I am putting one particular case, taking one particular case. So this is the truth table. So I have defined the function. So now for any input combination, I know what is going to be the value of the function. Okay, so that is what essentially the function should tell. There should be a well-defined output value which can only be either 0 or 1 for each combination possible at the input. Okay, there are 8 combinations possible at the output. Sorry, at the input, and then for each combination, is it a 0 or is it a 1? I need to specify that. So truth table specify that explicitly by listing out all the combinations which are possible. Okay, now I have well defined this Boolean function called f. Now the question is, how can I find out the Boolean expression for this? Okay, so to see how we can do it, there are multiple ways. I said you can write down the Boolean expression. In the last class, I tried to introduce that you can just do that by looking at the occurrences of 1 or by looking at the occurrences of 0. Okay, so now each input combination, okay, each input combination can be either 0 or 1. So if I look at all the cases where 1 is appearing, and then I can say that if output has to be 1, either it should be input should be 0, 0, 1, or it should be 0, 1, 0, or it should be 1, 0, 0, or it should be 1, 0, 1. Okay, so if I have to specify the occurrences of 1 as one of the many possibilities, I will, in order to discuss one of the many possibilities, if any of them becomes 1, I have an output 1. Then this is called that can be said with respect to OR operation, right? If one of the cases is 1, then multiple ways it can become 1 can be said as either this or this or this, etc. Okay, so let us look at all the possibilities where it can be 1. So this, it can be 1. These are the 4 cases it can be 1. Now if you look at how do we get this 1, so if you want to explicitly talk about this one particular case where it becomes 1, you need to have 3 possibilities happening at the same time. That is, A should be 0, B should be 0, and C should be 1. When all these 3 are satisfied, so how do we put that the logic that all 3 things has to be satisfied simultaneously? That is the case where we use AND operation. So AND operation basically tells you that each of the individual cases has to be satisfied. If all of them are satisfied, then only AND gate will give you output 1, right? Whereas OR gate, if either one is 1, then the OR gate will be either of the cases are satisfied, then output is 1. So the basic difference between AND operation and OR operation is that the AND operation insists that all the individual cases has to be satisfied, then only the output is going to be 1. Whereas in the case of OR operation, either one of the individual cases are satisfied, then you have the output 1. So this is the basic difference. So we are going to use that basic differences in order to write down first of all the case of individual cases of 1. So the first case 0 0 1. So A has to be 0. I can say A has to be 0 means A bar has to be 1, B bar has to be 1, and so I am doing an AND operation. I am insisting both should be satisfied. A bar should be 1, B bar should be 1, and C should be 1. Okay, because C here it is 1, value of C is 1 for this particular case. So this way I can write insist that all the cases, that is A equal to 0, B equal to 0 and C equal to 1, all these three requirements can be satisfied if this A bar dot B bar dot C is equal to 1. Okay, and similarly if I can write the next term, probably you can say this A bar dot B dot C bar, right? So when this product or this output of this, that is A bar dot B bar dot C, if that is equal to 1, that is the case which we are talking about, the first case. And then A bar dot B dot C bar equal to 1, then that is the case which the second case. And similarly the third case is basically A dot B bar dot C bar. That is another way in which one can come. And the final case where one appear is here. So that is A dot B bar dot C. So C equal to 1. So A equal to 1, B equal to 0 and C equal to 1. A equal to 1 and B equal to 0 and C equal to 1. So that is the fourth case. So these are the cases where I am writing the corresponding Boolean expression for individual cases. Okay, so in order to write the individual cases, how it can become 1, that is what I am writing. So if it has to become 1, then three things has to be satisfied, and that is A should be 1, B should be 0 and C should be 1. So another way we can say A should be 1, B bar should be 1 and C should be 1. Okay, so that way if you put the dot operator, I have the individual cases already. Now the next thing is that in order to write the complete expression, now the function can be 1 in 4 different ways, right? Because there are 4 ones at the final column. So there are 4 combinations which can give rise to 1. So I need to tell or when I write the Boolean expression, I need to tell either it could be this way or this way or this way or this way, it can become 1. So how do I say that? So I can write it like this: f of A B C can be written as A bar dot B bar dot C plus is OR operation. So this is one way it can become 1. Another way it can be 1 is A bar dot B dot C bar, or I can have another possibility satisfied, that is A B bar C bar, or even I can have the fourth possibility, that is A B bar dot C. So this is an alternate way in which I can express the Boolean function. So we are looking at how to express the Boolean function. Okay, how to represent the Boolean function? First I said you can write down all the input combination and the corresponding output. That is a very elaborate explicit way of writing it down, but you can also say by looking only at the cases where it becomes 1, and then express it as this particular format. So first I will use AND operation to tell all the individual cases where it becomes 1. In that case it has simultaneous criteria, that is A should be 0, B should be 0, and C should be 1. So that is the first case. So we are saying A bar should be 1, B bar should be 1, and C should be 1. So when all the 3 are satisfied, then only that becomes 1. Or then we say if A bar is 1, B is 1, and C bar is 1. Okay, if together these are satisfied, then also it can be 1. Or, so every time when we say or, we put the plus, and every time when we say and, we put the dot. Okay, so this is another way of specifying. So this is the only way the Boolean function can become 1. Either this become 1, the first term, or the second term become 1, or the third term become 1, or the fourth term become 1. So there are only 4 cases that will give rise to 1. So there will be 4 such terms like this, and each term has all the 3 variables present, either in direct form or in complement form. Okay, and there is a name for this way of writing down the Boolean expression. This is called the canonical. This is called canonical SOP form. Canonical SOP form. Okay, SOP stands for what? Sum of the product. Sum of the product. Each term individually, each term if you look at, it is a product. Basically we are referring product as the AND operations, and then sum as the OR operation. So sum of the products. So each one is a product term, and we are adding many product terms, right? Loosely speaking, we are adding them. Okay, actually it is not addition, it is basically OR operation, but loosely speaking you can call it as sum of the product. Okay, all right. So if that is the case, how can we make this representation even more concise? That means here we have to write all the 3 literals in each product term, and then we have to sum them up. Okay, if the number of ones are larger, then this term, this Boolean expression will also become bigger and bigger. Okay, so is there any way in which we can represent it in a more concise manner? Yes, you can represent it in the following manner. Okay, so this F, A, B, C can be written as by this notation sigma, and that then we will say which of the product terms. So every position, every combination of the input, there is a corresponding product term. But all the product terms are not present in the expression. We are only taking the case where it becomes 1. So we just need to specify the product terms which appears. Okay, so in this particular case, if I write, it will look like this, and I will tell you what this means. M1, then M2, M4, M5. Okay, so this is a more concise representation of the same function. Sigma means sum. Okay, this sums here, which is what we, okay, this is a sum, this is a sum, this is a sum. Okay, all the sums you can write it by using a sigma notation, and then individual product term is what I am referring here as M1. So this is basically M1. How does it become M1? I will tell you now. This is M2, and this is M4, and this is M5. Now, where M1, M2, M4 and M5 are the min terms. Okay, they are called the min terms. They are the min terms present for the given Boolean function. The min terms present for the given Boolean functions. So there are 8 min terms corresponding to each of the combination. So if I may write all the remaining cases, I can continue write the other cases also. So here if I write, it will be a bar dot b bar dot c bar. Here if I write, it will be a bar dot b dot c, and here if I write, it will be a b c bar, and here if I write, it is a dot b dot c. So these are the min terms. Okay, and if I name them, this is my m0 and this is my m1. Small m I am using. Okay, min terms we use small m, then m3, m4, m5, m6, m7, m01. Okay, I made a mistake. I missed m2. This is not correct. Okay, so after m1 it is m2, m3. So this is basically going in the order of our decimal representation of these combination. Oh, sorry, again m4, m5, m6 and m7. Okay, 0 to 7. Right, so decimal representation, you know, we have 0, 1, 2, 3. This is the binary code. 100 is the binary code for decimal digit 4. Then 5, 6, 7. So correspondingly, you use them as the subscript for the small m. So that corresponds to m0. So whenever we say m0, small m0, we mean this particular product term. Okay, each of the min term is a product term. Okay, and then we just need to specify, in order to specify the given Boolean function, you just need to specify which all min terms are 1. Okay, which all min terms are present means which all min terms are actually giving you 1 in the truth table. So that is what we are talking about. So if the min terms are given, then we can write down the truth table very quickly also. The opposite way we can also go, that is given the min term. So let's question, write the truth table for f of ab is equal to m0 m3. Okay, so the min term representation is given. Okay, now you can write down the truth table. Okay, so this is the opposite way you can go. So you have only 2 variables here in this question. So you have a, b, and then you have your f of a, b. 0, 0, the min term corresponding to that is m0. m0 is not m0 is present, so you give 1. Then 0, 1, that is m1. m1 is absent, so you put 0. 1, 0, that is m2. Min term is absent, so put 0. Then 1, 1, you have min term m3, so that is present. Okay, so m3 is also correspondingly 1. So in other words, I can say f of ab, what is written here, this form, I can show all the canonical terms, all the min terms. If I explicitly write, it is basically a bar dot b bar plus a dot b. Okay, so the 2 min terms are present. One is a bar b bar, other is a b. So this way you can go back and forth. Okay, so this is basically the canonical SOP form, sum of the product, and you can represent them concisely by using only listing of all the min terms that are present, and you use sigma notation to say that all these min terms are to be added up. Okay, in order to get the Boolean expression. Alright, so what is the other way we can represent the Boolean function? Alternatively, we can represent the same Boolean function in a slightly different way. So let's take the same example that we were looking at, f of ABC. We had what are the terms which I said are present? We have M1, M2, M4, M5. M1, M2, M1, M2, M4, M5. Okay, so these are the four terms that are present. So if I write the truth table again, A, B, and then C. So then I have f of A, B, C. So 0, 0, 0. M0 is absent, so I put 0, 0, 0, 1. Yes, that is M1 is present, so I put 1. Then I have 0, 1, 0. M2 is present, so that is 1. Then 0, 1, 1. M3 is absent, I put 0. Then 1, 0, 0. That is present. 1, 0, 1 present. 1, 1, 0 absent. Then 1, 1, 1. That is also absent. Okay. So it is the same Boolean function which we looked at little before. Now we are going to look at an alternate way to specify this Boolean expression. Okay, so how can we do that? Okay, so look at the occurrences of 0. How can you get the 0 from ABC? Okay, when A equal to 0, B equal to 0, C equal to 0, we should get a 0. Now we are looking all the cases of 0. So there are 4 cases of 0. So how can you first of all isolate the first case, that is when A equal to 0, B equal to 0, C equal to 0. I need a 0. All other cases if I have to, I want 1, but only in this particular case, that is A equal to 0, B equal to 0, C equal to 0, I should get 0. So how can I write the Boolean function just to isolate this particular case? So the one way, can I use AND gate? Yes, we can use AND gate also. That we have already seen. Okay, minterm is basically by using AND gate, but we mostly use that for the cases of isolating the output becoming 1. But when output becoming 0, it is better to use OR gate, because you see OR gate, if you the truth table of the OR gate which we earlier defined, so x, y and x plus y, or OR operation, you see 0, 0, I have 0. Then 0, 1, I will have 1, 1, 0, I have 1, then 1, 1 also I have 1. So you see that the distinct case here is this. Okay, there is only one case at which output becomes 0, that is when both are 0. Okay, so OR is a good operation which can isolate the case of 0. There is only one unique case where 0. And similarly, if you look at the AND gate truth table, that is good for isolating the case of 1. X dot y. So you have 0, 0, 0, 0, 1, 0. And 1, 0, 0. And then 1, 1, you have 0. Now 1, 1, you have 1. Right? So here you can see that AND gate can be used to pick out this one particular unique case, and similarly OR gate you can use to pick out this one particular. So output is 0 for OR gate in only one case, one combination. So even if it is a 3 variable, there will only be one combination which will give rise to 0. So what is that case here? If this particular case has to be 0, then how do we write it? Okay, that is simply so let me write, that is simply A plus B plus C. So if I write like this, 3 variables A plus B plus C, A OR operation, B OR operation, C. If all these A is 0, B is 0, C is 0, then only this is going to become 0. Just like I have told you here. OR operation has that inherent nature that it will distinguish one unique case where all the inputs are 0, then the output is 0. So here output is 0 when all these are 0. So that is quite easy. Now what about the next case of 0? How do I write it? I have to have this 0, this 0, this 0. So I can write it like this: a plus b bar plus c bar. I can write like this, right? So when a equal to 0 and b equal to 1, c equal to 1, right? When b equal to 1 means b bar equal to 0, and c equal to 1 means c bar equal to 0. So when individually each these terms are 0, then so we are insisting all of them to become 0, then only the entire term becomes 0. Okay, so this next one is a 0, then a bar. So a bar becomes 0, right? A is 1 and then b is also 1, so therefore b bar becomes 0 plus c, okay, c equal to 0. So that is the case where you get this, and the last case is basically a bar plus b bar plus c bar. Okay, so these are the individual cases. Each term basically pick out one combination. This term pick out the first combination, this term pick out the combination corresponding to this one, and this term pick out the combination corresponding to 6, and this term pick out the combination corresponding to 7. Okay, now similarly as before, I can write for all other terms also this, though they are not present for this particular function, I can list out them and then say that which all the, terms or these terms are called max terms. Okay, so let me write that max terms. Earlier we said min terms, now these are max terms. Alright, so what about 0, 0, 1? A plus b plus c bar. Next one, a plus b bar plus c. This one, a bar plus b plus c. This one, a bar plus b plus c bar. So these are the min terms corresponding to, so we can call this as capital M0, the next one capital M with a suffix 1, M2, M3, M4, M5, M6, M7. So these are the max terms. And now what about the Boolean function? How do we represent it? Okay, so once you know which all max terms are present, for example here this is present, this is present, this one is present, and this one is present. These are the max terms which are present, means the cases corresponding to 0 in the truth table. Okay, so we can write down f of a, b, c alternatively. It is the same function which we wrote earlier, but now we are saying a plus b plus c could be 0, or which could be 0, a plus b bar plus c bar could be 0, or a bar plus b bar plus c dot a bar plus b bar plus c bar. Okay, now here it is a AND operation I have taken. Okay, so individually they are basically sum, okay, or operation. Each term, if you look at, these are sum terms. Okay, so this is a sum term, this is another sum 1 I can call, then this is sum 2, this is sum 3, sum 4, and then we are taking the product of each of this sum term. So how do we call this? So this you can represent it as this dot operation I can write with this pi symbol, just like sigma I used for sum operation. The pi I will use for product operation, and then I will specify what are the terms which are present. So all the ticked one, so that is M0 dot, then next one is M3, then next one is M6, or so we are basically multiplying all the things, meaning AND operation of all these individual max terms, and then M7. So this means this M0 into M3 into M6 into M7. So this is what we mean when we write like this, okay, product of this. So this way of writing Boolean expression is called POS form, okay. This is called canonical POS form. So Boolean expression can be written, earlier I said canonical SOP form, now this is canonical POS form. So that means product of the sum. POS stands for product of sum. Okay, POS form. Okay, so what did we learn today? So how to represent Boolean function? First, by truth table I can list out all the different cases. That is the most simplest, but it is a bit lengthy way of representing a Boolean function. But then I can, looking at the case of 1, I can pick out the corresponding min term and then write it like a sum. Okay, so that is what we saw here. So this is M1 plus M2 plus M4 plus M5. So this sigma means this sum operation. Okay, so that is one way of specifying, a concise way of specifying this particular Boolean expression, which is called canonical SOP form. Then I said, like, alternatively you can write them as POS, that means product of sum. Each sum term is now called as the max term, and we use capital letters M with a suffix 0, capital M with suffix 1, etc. And then you look at the cases where it is 0, okay, and then corresponding max term you take, and then take a product. Now if any of them is 0, you know that when you have product, the entire function will become 0. But if it has to become 1, then you have to add them, or operation. If any of them has to be, if the output has to become 1, whenever any of them become 1, you just use OR operation. But for any of them to become, if the output has to become 0, when any of them becomes 0, you have to do the AND operation. Okay, so that's basically the difference. Now these are equivalent representation. Now another feature of these representation is that you can use AND gate and OR gate to implement this. Okay, so next thing is implementation of this function. How to implement these functions? Okay, so if at all we want to implement the SOP form, so let us now talk about implementation of Boolean function. Implementation. That means we are talking about the gate circuit which can implement this given Boolean function, how to build a circuit which can implement it. Okay, so if you look at the first expression, that is f of a b c is equal to, what did I say, m1 plus small m1 plus m2 plus m4 plus m5. Okay. So if I write the Boolean function in SOP form, so this is canonical SOP form, and if I want to implement it, each min term I can implement by using AND gate, and then I use an OR gate to combine all this min terms. Okay, that is plus operation I will implement with OR gate, and each min term m1, m2, m4, m5, each of them I can implement using AND gate. So I assume that the literals, that is A, B, are available in direct form and complement form, and that is easy usually to you can use 3. So let's say A, B, C, and then this is our A, and this is our B, and this is our C. So this line is basically corresponding to A input, and then I can have this just use a NOT gate and create this. Okay, this is the complement form. So in digital circuit usually A, B, C as well as A bar, B bar, C bar, these are available. From that we have to construct the given Boolean function. For example, the first one M1, how do I construct? I need to use an AND gate, and AND gate will have 3 inputs because each min term will have 3 literals, either direct form or so M1 means basically A bar, B bar and C. So I take so let me take A bar, then B bar. So this dot here means I am connecting. If there is no dot, there is no connection. A bar, B bar and C. Okay, so I use a AND gate. So this is basically my M1. Similarly, I can create M4, M2. M2 is what? M2 correspond to 0, 1, 0. So that is A bar, B, C bar. So A bar is here, A bar, B is this, and C bar. Okay, so that is M2. Then M4 is A, B bar, C bar. So that is here, A, B bar is here, C bar. M3 and M5 is A, B bar, A, B bar, C. A, this is A, then B bar, and then C. So that is M5. Okay, so we have generated M1, M2, M4, M5. Now what we have to do is basically use an OR gate to we need an OR gate which can do this. It's a 4 input OR gate, so that will give our f of A, B, C. Okay, so this particular function can be implemented in this manner. Now alternatively you can use the canonical POS form. So this is also equal to M0 dot, then M3 dot, M6 dot, M7. Okay, so same way I can implement the POS form also. So again I have A, then so I will use a more concise notation. So this also means the same thing. This is a more concise notation. So this is your A, and this is your B. You take without any bubble, it means B, and through a bubble if I take, it is B bar. and then next is C. Okay, so now I have to create a the max terms. So how do I create max term? I use OR gates. First one is what? A plus B plus C. So A is here, B is here, C is here. So I need to give a OR gate here. Okay, so now here it is, first one is OR gate, so that will give you M0. M3 is what? M3 is A, B bar, C bar. A plus B bar plus C bar. So A plus B bar, C bar. Another OR gate. So that will give you M3. Then M6, that is A bar, B bar, C. A bar, that is here, then B bar, and then C. So that is M6, and M7 is A bar plus B bar plus C bar. So that is A bar plus B bar plus C bar. So that is M7. So we generated all these max terms. Now what we need to do is we need to use a OR gate to take the OR operation or the sum operation. So that will give you, this is another alternate way. So depending upon the Boolean function, I have a different implementation. So that is the point. So implementation depends upon the Boolean expression. Okay, because looking at the Boolean expression will have basically AND operation, OR operation, and it can have complements, right? So complements are all available here. So the literals are available either in direct form or complement form. So literals means A or A bar, B or B bar, C or C bar. So each of the product term or sum term will have these literals available in direct form or complement form. For example, here all of them are A, B, C. In the second term you have A, B bar and C bars, but all the literals are present either in direct form or in complement form. Okay, so if they are available, you only need two levels. Okay, level 1 is this, so this is here level 1, and then level 2. Here also there is only two level, so this level 1, but level 1 is implemented here with OR gate, here level 1 is implemented with the AND gate, and then level 2. So these are two level implementation of the Boolean function from the inputs which are available in direct form and complement form. Okay, so if they are available like that, then we only require two levels.
Excuse me, sir.
Yes.
In the first circuit, sir, here shouldn't it be M4, sir? You have written M3 there.
Oh, acha. Yeah. I think I made a mistake. Yeah, you're right. So this is M4. I think I have written M3. So if it is M4, okay. So I think I only wrote it here like that, but the term that I have constructed is basically A, B bar, C bar, right? A, B bar, C bar. So that is M4 only.
Yes, sir. Yeah. Mistake in the notation, sir.
Oh, only the notation is different. Yeah.
Sir, yes. And also, sir, in the second circuit, sir. So that f of ABC, sir, it should be AND gate, no, sir?
Oh yes, correct. Correct.
Yes, sir. I got confused in that.
Yeah. You are right. This should be AND gate. Yes. I hope I don't make other mistakes here. Yeah, so these are not intentional, but sometimes it happens like that. Sorry for all of those mistakes. So basic idea is two-level implementation. You can use either POS form or SOP form. In POS form, we generate the sum terms first and then take the product. So that is so this is POS. Product of the sum. So here this is the product, this is P, and these are all sum. And whereas here this is SOP. So this is the sum, and then these are the product. Yes. So depending upon how many input variables are there, the number of inputs to the in SOP form, the number of inputs to the AND gate will be basically equal to the number of input variables. So if there are 3 input variable ABC, then you have 3 inputs. 3 input AND gates are required, and then the number of inputs to the OR gate in SOP form will depends upon number of minterms. So here minterms are 4, 1, 2, 3, 4, and therefore we have 4 input. Similarly in POS form, again the number of inputs to the OR gate depends upon the number of variables ABC, that is 3, and then the number of inputs to the AND gate, that is in the second level, it will depend upon the number of max terms. Okay. Alright, so let's have a break and then we will come back again.